GMAT all day.
For our final probability video, let's take a look at a question where it would actually make sense to use our 1 minus rule. This question says, 6 executives attend a corporate retreat with each executive accompanied by his or her spouse. All 12 of the attendees are automatically entered into a raffle in which each of their names is added into a hat and 4 names are selected to win a prize. If each name can only be chosen once, what is the probability that at least one couple has both members win a prize or win the raffle? So for this question, I probably start out, let's just write out what our couples look like. So let's say I have A and B are a couple, C and D are a couple, E and F are a couple, G and H are a couple, I and J, and K and L. These are my 6 couples, 12 people. When it comes to combination or probability questions, I find some of the hardest ones to be when they're talking about pairs of things, either pairs of people, or sometimes I've seen ones where they talk about handshakes, because I get confused between whether I should treat each of these couples as a single couple or as 2 people, and do I have to then multiply by 2 or divide by 2? And so to start, let's just say I want to visualize what my couples look like. These are my 6 pairs of couples. Then I'm selecting 4 of them to win a prize. And so I'm not selecting 4 couples, I'm selecting 4 individuals. Therefore, it is possible that 2 members of the same couple can each win a prize. That is what I am looking for. And so in this case, if we were to do what we did in the last problem and just write out what are the ways that I can get at least one couple where both members win a prize, that really means the probability of exactly one couple is picked, or that would be plus the probability that 2 couples are picked. Then once I've selected 2 couples, all 4 of my slots are filled. And therefore, there's no more possible outcomes. So now let's think, if we wanted to do what we did in the previous problem, just build our answer from the ground up, what would that look like? So if we are looking for pairs of people, what that means is the probability for the first person doesn't really matter. We cannot get a pair until the second person is chosen. So what it really means is, in terms of the first person, it's sort of like you're just looking for the probability of choosing a person, or the probability of one of your 12 people being chosen. So the probability that this first person is a person is just 12 out of 12, or 1. Now it is once you get to the second person that you can start thinking about our couple probability. So let's say the first person selected was A. It could have been any of our 12 people. Let's say we chose A here. So if we want the probability of, for example, exactly one couple wins, now we're looking for B to be chosen. So if I want to find the probability that B is chosen, but here is where we start running into an issue, because B does not have to be chosen here. B can be chosen here, or B can be chosen here. And so we'd have to find all of these probabilities. But then you might also see that E doesn't even really have to be chosen, because say we put C in this spot here. Well, now we can get B to pair with A, or we can get D to pair with C. And then when it comes to selecting D, D could come here, or D could come here. The same is true for B. And then on top of that, we also have the probability of 2 couples winning. And so once A is chosen here, then C is chosen here. So we don't have a pair, but it is still possible that we get our 2 pairs if B and D are chosen over here. And there are multiple ways that can happen. And so we have, if we're trying to build this from the ground up, there are a lot of moving parts, a lot of different components, and we would have to find all of the probability for all of those different scenarios and then add them up. And it could get very time consuming very fast. So what is another way we can think of the probability of choosing at least one couple? What we can think of it is the probability of choosing at least one couple is the same as 1 minus the probability of not selecting at least one couple, which really means 1 minus the probability of selecting no couples. And this is a much easier scenario to visualize. So we're not going to be doing this. Over here. No couples. So if we want to find this, we need to find the probability that we select no couples. That is not our answer though. We got to remember to do 1 minus this, and you could almost always expect that one of the trap answers would be if you had just selected this here, so don't do that. And so now let's talk about what would the probability of selecting a no couples look like. So for our first person, it's the same as before, right? We were just talking about the probability of selecting a person, which is 12 out of 12. So same thing. Let's say this first person is A. So if we are trying to find the probability that no couples are selected, we are now saying, okay, I just don't want a B. And so for my second person here, how many people do I have left? Once A is chosen, you have 11 people left. And how many of those people are not B? Well, 10 of them. So this should just be 10 out of 11. Let's say this person then here chosen is C. So far we have no couples. But now for this third slot here, we don't want to choose B and we don't want to choose a D either, because that would give us a pair with C and D. And so once A and C are chosen, we still have 10 out of our 12 people remaining. How many of those people are not B and are not D? Well, it should be just 8 people. And now maybe you can sort of see the pattern where our denominator is going down by 1 each time, and the numerator is going down by 2. Let's say this person here is E that is chosen. So now if we want to get no couples, we cannot select B, we cannot select D, and we cannot select F either for our final spot. So for our last spot here, we have 9 people remaining. How many of those people are not B, D, or F? Well, 6 of them. So this here should be our probability of selecting no couples, and it's really only one scenario that we need to take into account. And so now we just got to find what this is. So this is just 1 times 10 over 11 times 8 over 10. Maybe I'll keep this like this because I see that 10s cancel out here. Times 6 over 9, which is 2 out of 3. So this is really just 16 over 33. But remember, do not select that. This is not our answer choice. This would be the most tragic outcome, because this would mean you did all of your work, or I should say 99% of the work, and you did it right. And then you just sort of wasted that time because you selected the wrong answer choice and got 0 credit. Because our answer is 1 minus this. So 1 minus 16 over 33, that is really 33 over 33 minus 16 over 33. And our answer is 17 out of 33. A. Those are our probability videos. Understand and scenarios, understand or scenarios, understand your at least rule, use judgment to either just build your answer directly from the ground up or use the 1 minus principle. That should cover probability. See you in the next video series.